I'm gonna sing a little bit.
All right, cool. Zoom says it's good,
Zoom says it's good.
which means we should get an echo in like 10 seconds.
Yeah. Echo, echo, echo. Okay. All right. Yeah, because I once I sing a little bit.
Yep, there it goes.
Yay, we're here. Because once again, I'm not at home, so I'm just doing this through Zoom. Um, yeah. So anyway, we're here. We're live. We made it. Yay. And
Yay!
so let's see. Let me close some windows here so I can see what I'm doing. But welcome in everybody. If anybody is watching, anybody out there watching, I don't know. Maybe we'll get a few people here and there,
No,
but
it's okay. Remember, we always get views afterwards anyway.
yeah, so it's all good. But I will
I
have one
have
of these
people
things
watching
up.
after.
Yeah, like hi again. But I'll have everything up just in case. But we're gonna plow through the GOES magnetometer today.
Woo!
A,
Yay.
fa- a new favorite tool of Aurora Chasers, and it does have some uses, but it's got some limitations. And we wanted to talk about these limitations because it does cause some confusion out there. So I will pass it along. We'll just get rolling here. Which one of us want to share the screens?
How about the one that has the slideshow up?
Okay,
Not
instead
to
of the slide.
call single person
Yeah,
out. I
not
just
to
don't have
call
it up
out
yet.
Tanya.
Sorry, Tanya.
All right.
She's like, fine,
You can just do
fine.
the screen at least, and I'll
I
do,
am trying.
or we can like split some of it.
Yeah, let's do that.
Yeah, it's like fine. We'll do
We'll
it.
each take one and just go and yeah, let's take turns. I like that idea. Sorry for the enthusiasm.
Yeah,
Yeah, except
super
I'm trying
enthusiastic.
to start the slideshow. So,
Yeah,
and
it gets kind of weird.
yeah, that's all
How to
right. I
start
got
it.
it. All
Yeah.
right.
I will
Uh,
share a little live stream too while we're sitting here.
Yes, I will share because I
I
haven't
will do
shared
my
anything
booty
recently.
I have it going in
that,
the wrong
that we're
direction.
live.
Never fails. All right, there we go.
Okay,
Theoretically.
maybe.
There we go.
Yay! Yeah, we have it.
Anytime now.
So yes, GOES magnetometer data for aurora
And
chasing.
yeah, and we're going to talk specifically about use of that data for Aurora chasing because it could be showing many different things, but not everything is relevant to Aurora.
Yep. Just like we learned with about everything on this.
About literally every tool.
Yep. So start with basics. Earth has a magnetic field, and that's what magnetometers are actually measuring. The magnetosphere is a little bit more compressed on the day side because it's exposed to the solar wind. It's kind of meeting it head on. And it's more stretched out because it interacts with magnetic field of the solar wind. So it gets to be more stretched and tail-like, particularly under a very, very strong magnetic field with strong negative BZ. And this is what we are after as aurora chasers. We we care what's coming in, but we mostly care about catching that magnetic reconnection. So solar wind actually will pile up magnetic field lines on the night side where they get very close to each other and finally snap. And that snap actually reconfigures the entire magnetosphere from something like a teardrop to something more of, well, think about it as an apple, so to speak. Um,
I like
so
that. That's a good description.
two
A little
lobes.
more modular.
Yeah, not two lobes, but I think Tamitha is describing it more of a kind of slinky, but that's wrapped. So it's lines that are going nice and round and more round than a teardrop shaped. But in that process, we start to see aurora with beautiful, tall red rays. So that's what we want to catch. And we care about it, and that's what we want to capture on video if we're lucky, or at least on camera, or at least see it. So we do care when that reconfiguration actually happens. And what's there to tell us when it actually is happening? So Christian, do you want to take this one?
Yep, I got this one. So we've got our two magnetometers aboard GOES, one on east, one on the west side. These are geostationary satellites. They stay put. They follow the Earth as it rotates. So GOES East is always at 75 degrees west longitude, and likewise West is always at 137 degrees west longitude. This means you likely would want to pick one or the other, depending on where in the States you are, assuming you're in the States, because they're really the only side that has any of this. Would be cool to have a 4-point system, though. But the idea is you want to pick, if you're on the West Coast, you're going to want to pick GOES West more to kind of get a little better of a picture as to what the magnetic field's doing. Likewise, on the east side, we want to use GOES East instead. They sit at about 6.6 Earth radii outwards inside of the magnetosphere generally. That can be pushed inside a little bit more or outside the magnetosphere, so it just depends on what the solar wind is doing. I'd say I'm good on this slide.
We'll have some examples of that coming up.
Yes, so here we have the very good plot because it's got a lot of different things we're going to go over individually. So this is what we're generally looking at. We've got GOES 16, which as we just mentioned is blue. GOES 18 is red. It's pretty much that. So you find which one you're closer to, pick that one, and follow that line specifically. So that means Alaskans are better off picking the west side, and that means that us here in the East Coast Midwest are better with the eastern one.
They also sit around the equator, so they're not directly over United States. So what they see is a magnetic field as it's changing over the equator. And that's why locating where aurora actually is happening is next to impossible. Well, I would say impossible with GOES magnetometers. It's not going to tell you where it's going to happening, and there are some limitations to will it tell you when aurora is happening. And you see a classical picture for GOES magnetometers. Magnetic field is more compressed, so it's going to register as stronger at noon. This is N for both magnetometers. And it's conveniently labeled in different colors. So it is more compressed and magnetic field is stronger again. And it gets more stretched out. So it's not necessarily weaker, you're just registering it as more stretched. So it is a little weaker where the magnetometer is sitting, and it's not weaker all over the place. And you will also see the midnight. So you want the magnetometer to be very, very, very close to your midnight because that's going to show you kind of more accurate data when things happen as far as aurora goes. Because typically the start of aurora is very close to midnight. It's either just before midnight or very close to midnight in the magnetosphere. And if it happens to be when it's your midnight, great. If it happens when you're at 10 p.m., well, it's going to look a little different. But we're going to go through a little bit more details here with some things that you could see.
And then should we point out the Arject since they were on there, like what that is?
Yeah, there's another one actually. So, and we'll
Oh yeah, I
go
guess yeah.
in more details when
Yeah, you're
when
right.
it's sort of weird stuff in magnetosphere.
Yeah, that's right. I
So,
forgot about that.
okay, we have, first of all, we do have a substorm here, not just one substorm, but a couple of substorms. But this is to point what happens with a substorm, that depolarization when magnetic field snaps and gets more rounded instead of the really, really stretched teardrop. So you have the growth when magnetic field is getting, so to speak, weaker on the night side. And finally, it reaches a critical point, breaks, and reconnects and reconfigures the entire entire magnetosphere, actually. This was going on when GOES 16 was on the night side, right around midnight. So onset, the time when aurora started to happen, was probably very, very
Perfect.
close to when GOES was registering it, because sometimes that doesn't get to be the case. And you could see it when two plots of magnetometers do not align very well. One is ahead of another, so sometimes you see that substorm in one, then you're going to see it in another, because substorm does propagate, so it goes from one point to another, kind of spreads throughout the auroral oval, which is why you don't get that synchronous reaction of in both magnetometers. But that reaction is also very quick. We're talking about really 10 minutes time when aurora is going to be the brightest. And if you happen to miss it, well, you're probably going to be taking
See
pictures
you in
of
3
very
hours.
different aurora. Yep. Wait for a few hours, exactly. Like in this case, that's exactly when it happened. And this is probably the time when GOES 18, the red one, was very close to its own midnight, and that's why it registered that very nice depolarization, that very nice snap. So who's going to cover this one?
Yeah, so
All right. Oh, by all
it,
means.
yeah, basically, what this one is how location is very important as well. Um, of course, I can't see the image like as
Yeah,
big
it's
see it,
goes 8
but
is on one line, goes 9's on it. Well, it's past that
So
line.
this is, yep, so
It's hard to
this is
see.
the GOES, this is previous set, way previous set of magnetometers.
right,
Oh, there's
GOES
circles.
9 and
Okay.
GOES 8. This is their respective locations. It's very similar to what you would see with magnetometers that are currently in our orbit. And there's one that's coming in to replace, I think GOES 16. That couldn't be GOES 19. It's going through testing. It's already sending some magnetometer data. It's not publicly available yet, but that's coming. But this one is overlay of where magnetometers, the GOES satellites were in relationship to auroral oval. So this is actual data, what Aurora looked like from space, because it's ultraviolet imager. So Aurora actually has ultraviolet light in it, and you can detect it from space. And this was a capture of one of the substorms. So it started to glow, and this is probably very, very close to midnight when it happened. Midnight as in magnetic midnight. So that's a specific location in the magnetosphere. When you are located at it and going through the magnetic pole, you're going to see the sun on the other side. And as you can imagine, GOES 9 was very, very close to that station, to that position. So it registered Aurora pretty quickly as the snap and depolarization. So that plot looked like Aurora was happening. But it took some time for all that glow to reach GOES 8. So it did not show depolarization signature, the substorm signature, until sometime later. And
Almost 20 minutes, just for the
if you
reference, it looks like.
happen to be if you happen to be in between those two magnetometers, you're probably going to see reaction in one, but you're not going to see aurora for a while, for a few minutes. And then you're going to see aurora, and then you're going to see reaction in a second magnetometer. So they're not necessarily reacting at the same time. They're not showing aurora at the same time. And depending on where Aurora starts, where GOES magnetometers are, and where you are, you're going to see anything from either delay in that reaction, you're seeing Aurora and GOES is not reacting yet, or you could be waiting for a reaction before going out and you just might miss Aurora. So there are definitely limits, and knowing which station is close to you and which one you need to track helps, but one thing that's going to help you more is actually ground magnetometers, because they do react in real time. And if there is a magnetometer station that's very close to you, and we're lucky in the upper Midwest, that's not the case for many other locations, because we do have a line that's going to show a reaction, and it's going to pick up the aurora as it happening over us in
right,
Canada, of course,
yeah,
for us most
the
of the time.
The Churchill
And this is
line,
a secret for people on Twitter. Ground
yeah.
magnetometers are better than GOES. Just put that out
Yay!
there.
Because
Yay!
of this right here, this image right here kind of explains it right there. Like it's location based, really. Like you can be in the middle and you have to decide, like, how to read this.
I think we should pick
Also,
up this question after the fact, but Margaret asked how Glendale substorm chart compares with GOES. I think we should go back to that at the end, though, because that sounds like a fun comparison.
I was actually going to mention the Glendale app, because the Glendale app relies on ground magnetometers. So it's
Right,
going to tell you when substorm can be seen from the ground
It's more accurate.
magnetometers. It is all, yep, definitely. For GOES magnetometer, it really doesn't tell you where aurora is happening, where it's overhead. Ground magnetometers pick up that data, and because Glendale relies on ground magnetometers, for all the modeling and for all predictions, you're much better off with Glendale app, unless you really want to dive into ground magnetometers and look at the bunch of squiggly lines that are all lined up. It's fun, I'm not going to lie to you, but in the middle of the night when you want to pick one app, that pick will be the Glendale app. So we were going to
Yes.
cover that anyway, but there we go. So definitely useful. Is it everything? No. Does it have limitations? Absolutely. And knowing those limitations, knowing when you can monitor whether or not you are still seeing growth of the next substorm, as opposed to you seeing sort of recovery, that might be helpful if you don't have any other tools handy.
What she said.
Well said. Yep.
We're going to look at some weird stuff that you can see in magnetometers that will get you very, very confused. But hopefully after this, it's going to be more clear. And there's some fun stuff too.
That's a great way to phrase it.
Fun stuff.
Yay.
I can take first too.
Sure.
Yeah.
Arc jet maneuvers. I'm sure anyone that's looked at the GOES magnetometers have at least seen these partially on one or the other set. These are pretty much literally times when the GOES satellite needs to readjust altitude or where it's at. Basically, it needs to activate thrusters, and its magnetometers are either turned. I'm not actually sure if they're turned off or if they're affected so much they just stop the data coming from it. But the point is, the data can't be read during this time, and you have an extrapolation of where it started and where it could be at the end of it, and then you get the actual values measured again at the very end. So I usually, this is just my thoughts on it, I don't generally pay attention to the middle sections of the ArcJet. Once it's beginning, ignore it until the end, and then go ahead and resume where you were at. They are very inconveniently timed sometimes, especially during substorms, but as of some occasions, they're just inconvenient to have and don't really mean much. But they, in the terms of Aurora, mean, especially on a quiet time, they don't signify anything themselves. They are literally just, oh, we need to activate thrusters. That's going to affect the readings. No more magnetometer for now. Pretty simple. Magnetopause crossings. These are my particular favorite events.
These are fun. These are
Yes,
fun.
yes. They're probably the funnest events. I guess, okay, Tanya, that was an accurate description for them. So we'll use fun. These are fun because, as mentioned, the GOES magnetometers or the GOES satellites themselves sit at about 6.6-ish Earth radii outwards. That's decently far, and it does allow some protection with the magnetosphere, but during heavy CME impacts, like, for example, in May when we had constant impacts, that boundary can be pushed inward, and it can leave the GOES satellites exposed to the ambient solar wind outside of that. When this happens, you are going to see it
naked and afraid in the solar wind.
Yeah, and basically they're baking in the solar wind magnetic field, which, I mean, we generally see values anywhere from plus 100 to plus 150 or 200 for nanotesla for standard magnetic field values. This will drop into the negatives of that value, which is much worse on all of the equipment and really just in satellites in general. It adds drag and a bunch of different other effects, which on that note, you see at least two different ArcJet maneuvers here. Once the GOES magnetometer or GOES satellites are outside the magnetosphere so much, they generally lose altitude and need to be pushed back up, and that's where you get the ArcJets firing from there. So if you're looking at the beginning of this chart, you've got a just standard, quiet, normal magnetic field. Looks like there might have been a decent, quiet substorm on the May 10th side. This would have been before. And then you get the impacts, which is perfect because they were both positioned on the day side right in the noon area. So you get the basically the most efficient knockback effect, and you could see how far back they get or how far into the Earth the magnetosphere gets pushed, leaving the satellites exposed. So then you have them drop down, and then you have the same effects. You get the dipolarizations there, which is just the magnetic field rebounding from substorms that are occurring, and then you get that shield coming back out. So think of just a big bouncy sheet thing. Not really good with the metaphors, but the idea is you get the shield coming in and out, crossing in between and outside of and inside of the orbit of GOES satellites. And then you get all the fun, well, we'll do the sawtooth events after that, but you get all the fun substorms after that. But the idea is when you see it drop below zero, you know you are outside of the magnetopause, which means something has happened to cause that boundary to recede further inward towards Earth. I'll let someone else take the next two. Oh,
Oh, yeah, my favorite. So, those things are this is really more in on the order of weird things. This is completely normal, and I think we should pull up the actual plot. But those oscillations sometimes can be picked up by magnetometers. They are ultra low frequency waves. So magnetosphere and ionosphere have plasma. Plasma behaves slightly different, and there are different waves that propagate in it. And this is just one of the examples. And it is ultra low frequency waves, and the frequency can be picked up by magnetometers. Um, Unfortunately, it doesn't mean much for Aurora. They're just there.
womp womp.
Um, they're they're pretty cool, and you can actually go to a 6-hour plot and pick them up. So they typically happen on the day side. They're not seen on the night side. In this case, both magnetometers picked up those waves when they were on the day side. You could see them on the night, on in the dusk sector. So that's past noon, closer to the night. And when you are using magnetometers for North America, sometimes people do get a little bit confused as far as, well, what those wiggly things are. Those wiggly things are ultra low frequency waves. So they're on the kind of cool but weird.
Yes.
All
Cool or
right.
They're
weird.
very cool.
They're very cool. Yeah.
I mean, they look like instrumental errors or some weird thing, but they're real.
Yep.
Tanya bugged everybody at Swipsy to find that out too. True
She
story.
did.
And they
No
finally
crap.
said, no, this is normal. This is what magnetosphere does. And indeed, we've seen them quite a few times. And this happened to be a fairly quiet day. And you can tell that because we are close to about 100 nanotesla. So this is as cool of a day and quiet day as it can probably get. All right. So can you see substorms on the day side? Can you see the signature? Yes, you can. It gets trickier to interpret, and unfortunately, again, because magnetometers on GOES work better for North America, people who are in other locations where GOES covers the day side sometimes wonder whether or not that could be an option. Unfortunately, there are no magnetometers on other satellites that cover Asia, Europe, or Australia. So, well, Europe gets a little bit of coverage for GOES magnetometers when we happen to be in the night at the same time. But it gets trickier because you could see the substorm because substorm is a global reconfiguration of the magnetosphere. It will affect the day side. So you'll see very similar signature. There is a growth and there is a bounce back. So growth is decrease in magnetic field strength and it bounces back. That decrease is not because of the stretch. It really is the magnetopause. The magnetosphere is getting more compressed and GOES is exposed to areas that are closer to solar wind. That's where a magnetic field is a little bit not as strong as closer to Earth. So the stronger magnetic field kind of moves away, gets very close to solar wind, and then it reconfigures, it recovers to some degree. So in this case, GOES 18 happened to be very close to noon, so that's subsolar point. GOES 16 was in the dusk section. It was past noon, so it was closer to the evening. And because it was closer to the evening where the substorm actually started to happen, it registered the signature faster compared to GOES 18. So that's why you see that much of a delay. It takes a while for magnetosphere to reconfigure. It is a global event, but you want to catch it when it's close to you, not when it's on the day side. You could be seeing quite a delay, potentially significant delay between the substorm as it happens closer to you and the substorm that finally registers and goes. So if you're in the night side and GOES is on the day side, um,
Don't rely on
that's not a healthy relationship. We
it.
don't recommend it. It's too
We know
much of a
something about
long
unhealthy
distance
relationships
relationship.
here.
Yes, for too much of a long distance. I like that. It
they're on one
works.
side of
It
the earth, you're
works.
on the other.
Yeah, it can
Yeah, it's
work,
not
but
gonna
not
work
really.
out. And you see the arc jets here, and this is closer to midnight, so you start to pick up the typical substorm signature. So that's good. And there's another one here. Arc jet happened to be in this area, so that got things messed up a little bit, but you start to see more of a typical picture of the substorm when it's on the night side.
Actually, that's a good point there. It looks like GOES 18 missed a substorm in that case during that
Mhm.
arc jet.
Yeah.
Good
All
example of
right.
it messing things up. Our
Our
favorite subject.
Yeah. Steady magnetospheric convection. Oh yeah. This is a nice textbook example of it too. Um,
very textbook. Sometimes you get into conditions with solar wind when it's very steady. It's at marginal negative BZ or it's close to positive BZ with high BT, and you end up with no substorms.
yeah, it's like a flat line.
Well, that's a
It
good way of
is
phrasing it.
literally flat line. Um,
Pew.
at least in GOES magnetometers. You're not
Yeah.
going to see much here. You'll see maybe an occasional thing breaking through. So there could be sort of an attempt at depolarization, but not that much. What's going to help you is for comparison, the ground magnetometers, they're going to pick up the same signature, except in the stations that are close to you, you're going to see all those tiny flare-ups, and that does tell you that you've got steady convection going on. So there is energy transfer from the day side when magnetosphere encounters the solar wind, and then the magnetic lines get pushed back, reconnect in the magnetotail, and then all of it is flowing at the same rate as from the day side into the ionosphere. There is a debate whether or not it really is that steady because magnetometers are clearly not showing the steady pattern. They see the oscillations. So I think the term that's being explored right now is balanced reconnections.
I like that a
That-
lot better. I mean, it's
Yeah, it's
steady if you're looking
balanced.
at it over a long period of time. It's averaged to the
Yep.
same, but is it steady?
Not really. So
Hmm.
we're talking about balanced reconnection intervals. It's not really steady on the day side. It kind of happens in bursts, so it gets to be pretty much the same from what we know how reconnections work. It appears to be very similar to the night side. So this is what you see in solar wind data. So this is a 4-day plot, and the time that we cover is July 22nd. So this is that interval. And BZ was it was there. It was marginal negatives and wasn't particularly exciting. Aurora was definitely there. It will glow, but it will be not particularly exciting. So mostly kind of green and sort of bubbly, with occasional red rays, but nothing explosive and spectacular like we want to see. Are we good on this one? Anything
Yeah,
else
I'd
to add?
say if just to visualize for some people, because I know everyone saw the October 10th show, and at least here on the East Coast, we had SMC Aurora from a little after sunset. There was just a substorm that just started to end, and then we had SMC Aurora to almost 10:30. So if you're seeing the big green band and you see maybe a pillar every now and then or some red bands, then it goes back to that green band. It's not really doing much. That's your SMC Aurora. That's the signature and GOES magnetometers for it.
Well, it gets very interesting because SMC kind of comes in two different things. The classical definition in research literature is there is ongoing convection with no substorms. But for October 10th, we had a totally different beast.
we did. This guy right there. The next slide, sawtooth event. And this was interesting in one respect, because if I remember correctly, Tanya, in the research paper, the BZ for this was a bit larger than what a typical sawtooth event should have been. Like it was like minus 20-ish, I think is what it said, but this was like minus 45 for like a long time. So it's kind of like SMC but on steroids. I think that was our favorite little description of it. And it was neat because
Yeah.
it was almost on a 3 hour interval. Like every 3 hours, it like tipped, and you got those way more dramatic outbursts. And you can see in that GOES plot pretty actually you you see the magnetopause crossing pretty clearly. And then it goes into what kind of looks like a sawtooth that up and down and up and down almost every 3 hours. Um, that's pretty cool. Like it's neat to see like these more textbook examples like that. But yeah, there's there's my really quick and dirty of it.
Oh,
That's
that's
accurate. Yeah.
actually very accurate description. And what's interesting for sawtooth events is you do have particle flux that's intensifying, and that correlates with the this depolarization. And then you have ongoing flux that's decreasing over time. So there is injection that happens, and that's exactly what drives Aurora. And Aurora Oval is globally enhanced. So you have very wide area of Aurora Oval that is lit up in between those sawtooth events. And you think that particles are going in, so Aurora should be showing up, but because there's not a whole lot of them that are coming in, they have to get to the denser layers of atmosphere, and that's where they start to show up as green. So you don't have interactions in the upper layers because of the density. It's not as dense up there, so oxygen is kind of waiting and nothing is happening. But when it's a little bit more flow, you start to see the red rays. But when there's a little bit of flux going on, it kind of has to go to the lower layers to encounter a little bit more particle molecules and just neutral atmosphere sometimes.
There's lots of traffic down that way.
Yeah, yeah. When there is not a lot of traffic, there are not a lot of collisions, so you don't see red. But you get down there and it's a little bit more congested, you start to see the green. And that's why you get the green in between those sawtooth events, and then you finally get the explosion. And usually, again, because those sawtooth, that depolarization event by itself is very short. We're talking about 10 minutes. That's why those rays just don't last very long. They're
Right.
gone pretty quickly. And you
Yeah.
get the brightening of the auroral oval um, it with a typical onset. So there's going to be one area that kind of starts it all and then it spreads out and then quickly sort of turns on and we're back to the green and bubbly stuff.
I had enough time to scream and almost lose my voice in that 10 minutes at the 1:30 UTC storm, then
It
was
was
gone into just a fade of color everywhere else, but no real structure.
it was good though for that 10 minutes.
Oh yeah. It was so easily the third brightest show I've ever seen, and that's knocking down a lot of shows in Alaska I've seen too.
All right. And I think that's what we got.
All right. Yeah, that's kind of the quick and not it's kind of quick and dirty on GOES
Yeah,
Magnetometer.
the
But
breakdown.
yeah, the breakdown. But it's nice to go over because we see a lot of, people trying to use it, and you get a little bit of the like the UL or ultra low freq ULF caused some confusion on Twitter. So, it's one of those things. It's like it's nice to have like a little powwow as to, how to use this GOES magnetometer and what it's how you can use it and knowing its limitations, because like
Yep.
everything in our world of aurora chasing, we have a lot of data and things at our disposal, but none of them are really for aurora chasing. So we have to
Our own
adapt.
interpretations.
Yeah. And then the more you can learn about the limitations of it, the better off you can use it, because then you know when you can use it and how. And so yeah, that was our whole little goal for today. So
Well, we
Especially
can,
since we've got our Tuesday show.
yeah,
yeah, we can definitely pull up the real-time plot and show a few things there.
yeah, go for it.
All right.
We'll put it to the real-time test here.
Yep. Let's call different things. So
Yeah.
from the right there, bright and yellow arc jet, and that's the orbit correction. And right now we have, let's switch to the 1 day. That's gonna, ooh, I see some oscillations there right there.
Yep.
But oh, we got goes going into the night side. So you see a decrease from noon to basically the nighttime, sort of decrease in the field strength that is sensed by the magnetometers. Nothing too exciting going on except for maybe this area. So I'm just going to magnify it to see if we're picking up the ultra low frequency waves. And we are indeed picking them up a little bit. So that's kind of interesting. They do show up in more areas than you would think. And just looking at a 7-day plot or a 3-day plot, you're not going to see them.
It's too
So,
small of an amplitude. No.
yep. But overall, if you want to switch to 6 hours and see what's happening in real time, this
It's
convenient
pretty quiet.
marker will tell you that not a whole lot is happening. And I think that would be, I think we have a reason why. So it's always good to correlate what's happening in magnetometers with solar wind data because the solar wind data will tell you what's coming and you can to some degree anticipate what's going to happen in magnetometers. So we have a,
Boo.
yeah,
Lame.
not much is happening. There is a little bit of a negative BC that's incoming, so we might see reaction from magnetometers, but for now, it's not long enough. So,
Yeah, it's a lot of
eh,
just this up and down.
Looks
we
like a
gotta,
mostly positive field too. Probably
yeah, we
Coronal
got
hole.
what?
Would you
eh,
enable BX for me?
Yep,
Let's see if that's a big component there.
yeah,
Yep, yep. Big negative, so we got a positive. It's probably either the traces, and that's kind of what I was expecting over the last couple of days with that big kernel hole in the northern hemisphere. It looked like it was a bit high, but it was going to be tracing out a good deal over the last couple of days of just some CIR component mixed with quiet solar winds. So the mostly BX component makes sense, the radial component.
yeah. And solar orbit data, that's sort of our incoming, what's going to happen in the next couple days. It's not looking particularly spectacular, so yep, we just have to wait for sun to do something more interesting.
Well, the good news is it's still kind of full moon week. So if it's gonna do it, this is a week to do it.
Yeah,
Unless
So
you're in
there's like,
Alaska, in which case have fun.
yeah, that's true. Unless you're up there
Or Scandinavia,
where you
anywhere
where
in there.
and it's fine. But I'm not jealous or anything.
No, not at all. Mm-mm.
Never.
We don't always want to be up in the Arctic area. Not at all. Nope. Nope. Are
So
we allowed
anyway,
to be
that's
this sarcastic online?
we do whatever we want. This is our show. So be as snarky as you want. I don't care.
Fair point.
But we're also getting back at what are we? We're coming into December, so we're back in the solstice. So we're gonna lose the RM effect, Russell McFerrin effect on the smaller scale stuff. Um, so I don't know. We'll see if we get any cool CMEs headed our way within the next couple months or something.
On that note, just for a
Spice
quick
things
note,
up.
solar weather is pretty much dead. We have very, very, very simple sunspots right now. Do not expect any eruptions or any impressive events over the next several days.
Now that you said that, though, watch,
I meant to jinx it. I really hope it works.
watch one of
But
them.
legitimately, odds are low. I would say even an M class flare would be a little surprising right
Okay. Well, there you go. There's our forecast for the week. Fun times. Anyway, hopefully anybody watching got a little bit of something out of this because it's interesting. It's cool that we have these things to use. We should probably just roll into after our guest speaker this week. Maybe we'll roll into magnetometers, ground magnetometers,
now. I'm down
and
for it.
to follow this one up. So then you can have the comparison of like how the goes and then using the actual ground
We
based
need to do a
magnetometer.
ground magnetometer series, I think. It
Yeah,
really would make sense, I think, to give it at least a couple shows for that.
yeah, because
yep.
it's powerful. It really is. Like
But it's a lot.
when you can look at the Z component and tell where the oval is, that's pretty cool.
There's a meme for that with like looking at solar wind data that the heads blowing up thing. I don't know. I'm too old for the memes there, but the blowing up head memes of the better data you get, and the end of it is using the Z component for
Yeah,
finding out where the substorm wedge is at.
yeah, it's pretty wicked. It's cool. So
Yep.
anyway, we'll
All
let you
right.
we'll let you all be. I will turn this off of YouTube, but thanks for joining.
Take it easy, everybody.
We'll see you in a couple days for our lovely guest speaker, which I'm super excited about. So, yay! All right. Have a good night.
Bye.
Bye.
Oh, hold on. And then I messed that up. So, because I'm on my laptop. Okay, for real now. Adios.